Okay, thank you. So I'm going to be talking about scrambling time and black holes, and much of the talk is going to be based on these two papers from, I guess, 4 years ago or so. And yeah, so the first thing I want to say is that I figured since this conference included both quantum gravity and quantum information, this would be a good place to talk about these things. So what we're going to do is we're going to start with a thought experiment of Hayden and Preskill, which is really the motivation for this. So Hayden and Preskill. And Preskill thought experiment. So we have a black hole here. And this is supposed to be the event horizon. And Bob has a qubit. And also, Bob knows the exact state of the black hole. Okay, so this is clearly an impractical thought experiment. But what Bob does is he tosses the qubit in the black hole. Okay, so then after that, he waits for Hawking radiation to come out. And I should say this is an unknown qubit. And it turns out that if you gather Hawking radiation from this, you can deduce the state of the qubit you threw in. So deduces state of qubit. And then he dives in with a copy of the qubit. And now, the question is, why hasn't he cloned the qubit? So, what Hayden and Preskill did to resolve the question is the first thing, if Bob, and let's say the black hole has mass m in Planck units. If Bob waits longer than m log m with some constant time, he can never catch up with a qubit. And I really should draw a Penrose diagram for this, but I'm really bad at drawing Penrose diagrams. So the point is that the qubit hits the singularity at the center before Bob can ever catch up with it. At least if it's a Schwarzschild black hole. So to recover the state of the qubit, he needs to wait at least something called the scrambling time. At least scrambling time. And from this, you can deduce the scrambling time. In order to avoid paradoxes from Bob being able to clone a qubit, you can deduce the scrambling time is greater than Cm log m for some constant c. So this was Hayden and Preskill's paper. And now what happened after that was Sakino and Susskind wrote a follow-up paper in which they made the conjecture that black hole scrambling time is order m log m, and that this is the fastest possible scrambler. Now, okay. So what happened after that was that there were a lot more papers with scrambling time. You know, talking about scrambling time, talking about how black holes might have the fastest possible scrambling time and everything. But the thing is, the scrambling time is not defined. It is not easily defined, or at least if you say scrambling time, a bunch of these papers had different definitions of scrambling time. And nobody seemed to pay much attention to that. And I still think people are not paying much attention to that. But what I want to show in this talk, I want to show one, the scrambling time of a system can depend radically, so can depend on the exact definition. And we have an example of a system where the scrambling time for given one definition is logarithmic, and the scrambling time given another definition is linear. So so the scrambling time for one definition is exponentially larger than the scrambling time for another, which means that really when you make this conjecture, you should be very careful about how you define scrambling time. And two, black hole scrambling time really depends on the definition. Could be m log m according to one definition, or I want to say m squared, but I think all we really can show is it's at least m squared according to another definition. It probably is exactly m squared according to the second definition, but I don't think anybody has shown this. And of course, we don't really know the dynamics of black holes, so we have to assume assuming, let's say, non-radical physics. So I will get to what this means later. Yeah?
So to define this time, this is defined for observable outside the black hole. We make the definition. I assume you have to say this is defined for which observer. Which observer?
That's right. We're trying to define it for an observer outside the black hole because really Bob is the one who's waiting outside the black hole and collecting the Hawking radiation. And so he's an observer outside the black hole, and he needs to know the scrambling time for this definition. Okay. So let's say definition 1 is the out-of-time order correlator. I'm sure a lot of you know what this is, but I'm going to give an intuitive explanation and then a real definition. So out-of-time order correlator is you have a system, and you have two parts, and let's say time goes up, and you have an operator you apply at point x at time t1, and now you wait. And now you operator at time y, at space y and time t2, and then you're going to take the commutator of these. So what that does is you apply the operator, you wait, you apply the operator 2, and now you reverse time evolution. You apply the inverse of operator 1, and then you apply the you move it forward, move time forward again, and apply the inverse of operator 2. And, or rather, O of x t1, O of x t2 minus O of x t2, O of x t1. So if the information from here doesn't get there, then this is exactly the same as this, and it's 0. If the information from here gets to here and operator 2 depends on what you did at operator 1, then this will not be 0. So the actual definition is 1/2 the commutator O1 x0 O2 yt, and now we want to square this, and one way we square this is just multiply it by its conjugate transpose, 2 of yt transpose. And this is the out-of-time order correlator. Okay, so that's definition 1. If the out-of-time order correlator has, it's going to have some value as t goes to infinity. Actually, I'm sorry, it's going to have some value as t2 has some value as t2 minus t1 goes to infinity. And if it approaches that value, then we'd say this is the scrambling time. So the time you have to wait for the out-of-time ordered correlator to, equilibrate. So that's definition 1.
Peter, are you taking a trace or a norm, or you just want to have that? Because these are still operators, right? So
Yeah, I probably should put a trace to really
make it about.
make it robust.
Does the definition depend on x and y?
What?
Where does x and y come into the?
Well, I mean, so out of time order correlator is at 2 points some distance apart, and at 2 times, and we might as well make the first time 0, some distance apart, and this, yeah, so for any 2 points in space-time, you'll have an out-of-time order correlator between them.
But am I taking like a max over x and y, or like if they're further away, I need to wait longer?
Take an expectation.
Expectation over x and y.
Yeah. I mean, I don't really think how you do it matters that much. You'll get roughly the same results. And I'm sure different papers have defined this slightly differently. Okay. So what is the second definition? Second definition is entanglement scrambling. So what we're going to do is we're going to start a system with 2 halves. We'll call them 2 halves, A and B, and row sub A, row sub B are relatively unentangled, not very entangled. I mean, if this is a quantum field theory, any system here is going to be entangled with any other system here, but they don't have to be very entangled. There's just the amount of entanglement proportional to the size of the boundary between them. Whereas you can imagine that they are maximally entangled where the amount of entanglement is proportional to the volumes. Let A, B evolve. Scrambling time is when psi AB trace A is maximal. Ooh, I should. Or at least when it reaches its equilibrium value as time goes to infinity. So you're taking this system, you're starting with in an unentangled state, and you're letting it evolve until you get a maximally entangled state, and that's the scrambling time. Okay. So the next thing I want to do is try to explain our toy model, which shows these 2 scrambling times can be radically different. Toy model is going to be a binary tree. And we apply Well, qubits on the edges are and qubits on vertices and dynamics apply sequence of random operators to edges. And if you like, you can assume the random operators are in the Clifford group, but you don't have to. Okay. So here's our binary tree. And we need an operator to apply to one node at time 0 and an operator to apply at another node at time t. So what we're going to do is we're going to take sigma x 0 and apply it to this vertex, and maybe another, it doesn't matter what, sigma x t, and apply it to this vertex. Okay.
So for this random operators, you just take a random unitary in U2 according to Haar measure.
Yeah, you can take a random unitary in U2 according to the Haar measure and apply it to a random edge. And actually, the way we do it in our paper is apply random unitary to edges with, using Poisson process rate 1. So in time 1, in unit time, the expected number of unitaries applied to any edge is order of 1. And you can assume that these unitaries are all in the Pauli group, although it doesn't matter, or not the Pauli group, the Clifford group, although it doesn't matter, you're going to get the same result either way. Okay, so what happens? Okay, so after time t are after, after, let's say, k unitaries, we're going to get uk minus 1 through u1 dagger sigma x u1 u2 through uk. So this is going to be some tensor product of Pauli's. Because u sub I dagger sigma something ui is Pauli. And, applying elements in the Clifford group, random elements in the Clifford group is exactly equivalent to applying random unitaries with a hard measure, so we can assume these are in the Clifford group. So what happens? Well, let's look at a pair of edges, or rather an edge joined by a pair of vertices. And UI sigma 1, sigma 2, UI dagger is going to be equal to, well, if UI1 and UI2 are the identity, this is the identity. So it's the identity if sigma 1, sigma 2 equals identity. Next thing I want to say is it doesn't matter which Pauli matrix it is by symmetry. So it's going to be N, I, N, and N are the other possibilities. N is non-identity sigma matrix, sigma star matrix, and this is this is 1 over 5, which is equal to 3 over 15. This is also 1 over 5, 3 over 15, and this is I want to say 3 over 5, which is equal to 9 over 15. So why is this? Well, there are 15 pairs of Pauli matrices which are not the identity, and exactly 3 of them are of the form Ni, exactly 3 of them are of the form In, and exactly 9 of them are of the form Nn. And you can easily find the equivalent probabilities if we had, instead of the Pauli matrices, the Pauli matrices on a dimension d qubit bit, and that's actually what we do in our paper, but this is exactly the same thing. So this is a nice dynamic process.
Peter, should the denominator be 16 rather than 15?
This is the 1 over 16,
Yeah.
the II.
Oh.
So you're never going to get II if you don't start with II. So this is the 1/16th, and these add up to 15/16, so so all the probabilities add up. So this is a nice dynamic process we can analyze. So basically, it's a binary tree, and each element has N, I, N, 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 I. Each vertex has an I or an N, and at time and here I want to make all of these other ones I. At any time, choose an edge. If it's not I, replace labels with IN, NI, NN with the appropriate probabilities. And the question is, how long does it take, starting with one N and everything else I's, does it take N to reach this point? Okay. Oh. If 2 points or 2 vertices have distance d, takes time, well, I'm just going to say order of d to reach the x, y to reach, for this process to reach y and have y become an n. And the proof ignore all n's that are not the closest n to I. So here, if you just take this n and pretend that all of these are i's, then, if this edge is selected and there's an n here, then the n moves 1, and it doesn't matter what, what the previous thing, it doesn't matter what the labels on these are, because this is only going to move forward if this edge is selected and it becomes IN or NN. And this N is only going to move backward if this edge is selected and it becomes NI. So you can only consider the leading N and do that, and that's just a random walk. And then once you've gotten here, you can do the same thing. Just look at the, look at the vertices that are close to, only consider the ends which are closest to this endpoint, and then you will, the same argument says that those are all you need to consider. And so now this is just a very elementary random walk, and you can compute exactly how fast it gets here, and it's linear time. So that says the out-of-time order correlator for the binary tree with this dynamic process on it is linear time. Now there's a very simple thing. How much time until entanglement scrambling?
But can I clarify, do you update all the edges per time step or a random one per time step?
Well, for every unit time, so for every unit time, so suppose you have, k edges. then each edge gets updated randomly there's a some process with time 1/k.
Oh, okay.
So there's some definite order in which you're doing the updates, but it's not like you're doing updates for each edge at unit. I mean, it's not like you choose one edge per unit time in the whole tree. You choose roughly k edges per unit time in the whole tree if there are k edges total. So for entanglement scrambling, you need for maximum entanglement, need, I want to say, 2 to the n minus 1 minus 1 qubits on left, and 2 to the n minus 1 minus 1 qubits on the right. So you have a bottleneck, and you need to get this maximally entangled, you need to get all the amount of information on the left over to the right and vice versa. And only one bit of information can pass this edge per unit time on average. So that means you need 2 to the n minus 1 time to scramble for entanglement scrambling. Okay. And we're going to use exactly the same arguments for our black hole, and I am running out of time. Or maybe not running out of time, but so now we're going to start talking about the black hole. And black holes have Hawking radiation. And assumption.
Sorry, other question?
What?
The first operation, is that the OTOC or?
Oh, yeah, this is OTOC is order n, where n is the depth of the tree. Actually, 2n. And for entanglement scrambling, you need 2 to the n minus 1. So black holes have a photon sphere. So here's the horizon, and here is the photon sphere. At exactly 1.5 times the size of the horizon, and the photon sphere is defined as the minimum orbit that a light ray can go around the black hole. And it's an unstable orbit, in case you're curious. So if you put a photon in this orbit, at some point it will either spiral out to infinity or into the black hole, unless you basically balanced it on the knife edge. But that doesn't matter. And what we're going to do is we're going to divide the black hole into cells. Divide photon sphere into cells. And this is I think this is a really interesting division of the photon sphere into cells. And so let's take the cell. It will look something like this. And we'll expand it. And its vertical radius will be h. well, CH, where H is the height above horizon. And its angular radius, or angular distance, will be root h times m, where m is the mass of the black hole. And these cells have some really nice properties. Okay. Temperature of the Hawking radiation at height h is 1/4 pi, I believe, square root of 2mh. And the entropy of radiation is, okay, 4 pi squared over 45 VT cubed. And if you put these two together, the entropy of radiation in any cell is order of what? Okay. Also, time to cross from one side of the cell to the other and back, measured by an outside observer, this is really nice. So we do there. So that's one side of the cell and back, and we can also compute the time it takes to cross and back on the same other side is the same for all cells. And it's actually order of m. So if you look at the Hawking radiation from an outside observer's point, of view, well, each of these cells is, I'm really drawing this badly, but each of these cells has, essentially the same amount of action in it, and it's fairly simple. So I want to say assume scrambling is carried out by Hawking radiation. And some people might object that Hawking radiation is really virtual radiation, but real information can be carried by virtual radiation, so there's no reason that scrambling can't be done by virtual radiation. How much scrambling can be done? Okay. So let's do the out-of-time order of correlation first. If you start here and have a light ray go from the surface of the horizon around to the surface of the horizon, this takes O of m log m time. It passes through log m cells. Why is that? Well, there are log m layers of cells around here. And it passes through constant number of cells on each layer. So it passes through order of log n cells. Each time it passes through a cell, it takes order of m time according to an outside observer. So the out-of-time order correlation is presumably order of m log m. I realize there are some details to make this argument rigorous. Okay. Now the other question is, how about entanglement scrambling? Well, divide black hole into two hemispheres. And what do we get when we do this? The cross section is going to look like M cells. Now there's another layer after this, which is, it's twice as thick and has half as many cells in it. So roughly M over 2 cells. Actually, it's not exactly half as thick. It's geometric. The next one is twice as thick and has half as many cells. So this is M over 4 cells. So when you add up this geometric series, which I think I should not, you get order of M cells in this cross section. You need to get M squared amount of information from the top to the bottom and vice versa to have entanglement scrambling. Entanglement scrambling requires m squared over m time. So rather than actually, I need to add another m time because each time a bit of information goes from one cell to the next, it takes m time for the outside observer. So this is m squared time. So according to this entanglement scrambling, according to this argument, entanglement scrambling in a black hole is going to have to take much longer than the out-of-time order correlation time. Okay. So that is roughly the argument. I want to say a couple more things. First, I really like this division of the black hole into the black hole photon sphere into cells, and I'm wondering if there's anything else it could be used for. Second, I've been thinking, is there some way to save complementarity for this? Because what we don't know is we don't know where the Hawking radiation comes from. If Hawking radiation is random, the information does not escape. If the Hawking radiation comes from the horizon, and depends somehow on what went in at that point in the horizon, this explains how information gets out. And it doesn't use any, it doesn't use any transmission of information faster than light except what's going on the horizon. It doesn't use any weird non-locality. And you can imagine that somehow there's some kind of vacuum fluctuations at the horizon that let information, information that came in at a point of the horizon get released at the same point on the horizon at some time indefinitely in the future. And this is incredibly speculative, but I don't know of any better explanation of how Hawking radiation carries information about stuff that fell into the black hole. And we can also explain exactly why, well, okay. No, that's not what I wanted to say. Okay, so I think I'll end here.